Selecting the appropriate model. Suppose that the analyst wants to model the company's sales. The first step is to identify the factors that have explanatory power on sales. In other words, factors that drive a company's sales. So the analyst might first ask, maybe it's GDP and or the exchange rate. So if that's the case, where sales depends on these external factors, the analyst may want to use a multiple linear regression. So the way this would be set up is as follows. So sales would be dependent upon what's happening with GDP and the exchange rate. Now, the second question that may be asked is sales perhaps simply a function of time? So for example, when a new product is launched, things like GDP and the exchange rate have no effect on that because that product is sort of gaining traction in the industry. So it's going to have its own trend line over time, irrespective of what's happening to GDP. So if that's the case, where we just expect sales of this new product to grow over time, we may want to use a trend model. Now, if the analyst projects that the sales might be changing by a constant amount each year, she may want to use a linear trend. So there it is. So sales, dollar sales, would simply be a function of time, and B1 here would just be the change in sales per period. However, sales do not usually change by a constant amount. Instead, sales usually change by a constant rate. In other words, a constant percentage. So if that's the case, the analyst may want to use a log linear trend, in which case we're plotting the percentage change in sales over time. And therefore the B1 would be the percentage change in sales per period. So you can see it's a trend model and log linear are very similar, except log linear is projecting percentage change in sales, whereas trend model is just projecting absolute value of sales or dollar sales. And the other thing you have to remember with these log models is, yes, it's true, they're measuring percentage change, but that percentage change is computed using continuous compounding. Part C. So assuming that the analyst sets up a trend model, if she notices that the trend model is producing serial correlation among the errors, it may be an indication that sales in the current period is dependent on prior or lagged values of sales. So here's the storyline for part C. If the current sales is dependent on what happened to prior sales, that would mean the sales now is correlated with what happened with sales in the prior period. But if your model is not capturing that correlation will instead be reflected in the error terms. And that's the issue here. So if you notice that there's a correlation among the errors, it means that the model is missing something. So if that's the case, the analyst may want to use an autoregressive time series model. So since we said sales is really dependent upon what happened to prior values of sales, why not model sales as a function of its lagged values? And there it is. So this would be your autoregressive time series model. Now, what are the conditions to use the autoregressive time series model? So first of all, the variable, which in this case is sales, must be covariance stationary. In other words, it has to have a constant mean and variance. Now, to meet this condition, the beta 1 coefficient, which is right there, must have a value that's less than 1. And we've covered this in previous modules, because if it was greater than 1, then that would mean sales in the subsequent period would always be higher than the previous period. On the other hand, if it is less than 1, we also determined from a previous module that sales would have a mean reverting level, and therefore it would be covariance stationary. Part 2. So again, these are conditions for using the autoregressive model. If there is still a significant correlation among the error terms or the residuals, then we have to add more lagged values. So for example, if we're looking at quarterly sales, and we're looking at a retailer, then we know for a retailer, every holiday season they have a spike in sales. So rather than having current sales simply a function of what happened to sales in the previous quarter, let's also see what happened 4 quarters ago, right? So what we want is we want the model to be capturing these correlations to prior values rather than the errors. So by adding this lagged value or the seasonal lag, now the model is capturing what happened 4 quarters ago. Step 2. The model is only valid if the errors meet the following conditions. And let me just stop right here, because I know we're covering a lot of stuff here in this module. But you got to remember this. When we're looking at a regression model, we want the errors to be random, because if the errors exhibit a pattern, it means that the model is missing something. So usually the first place that the analysts look at after the software produces the regression model is they look at the errors, because if they see anything funny in the errors, they won't even bother looking at the model. So here it is. So what is it you're looking for in the errors? Well, the expected value of the errors should be 0. That's not to say that there should be no errors. Instead, what this says is some errors will be positive, some errors will be negative. So when you average it out, it's 0. The second condition is that the errors should be normally distributed. Third condition is the errors should not be serially correlated, and we discussed that right there. Again, if the errors are exhibiting correlation, it means there's this relationship that the model is not capturing. Okay. And finally, the errors should have a constant variance. That's referred to as homoscedasticity. And as I said before, if the errors are picking up a pattern, it implies that the model is missing something. And what I do here is I show you a framework to illustrate that point. So here's y, here's the value or the variable that we're observing, and here's our model. So anything, so the variation in y is either explained by the model, or if it's not explained by the model, it's going to be captured by the errors. So that's why analysts first look at the errors, and if the errors are capturing a pattern, it means the model is missing something. Okay? And this really is the basis for the ANOVA tables we've looked at, so analysis of variance, where we break down the variation in y to the part that's explained by the model and the part that's explained by the errors. Step 3. A model with a strong explanatory power will exhibit the following characteristics. And let me just pause right there. There's 2 key words here, and they mean different things. So first of all, for a model to be valid, we're looking at the errors, and they should be random. So if the errors are random, that just means the model was correctly specified. But just because a model is correctly specified doesn't mean it has a strong explanatory power, right? And that's why we look at step 3. So by the time you get to step 3, you're saying, yes, the errors are random, so the model was constructed properly, but now let's see how well this model explains this dependent variable. So now you look at some other metrics. So a strong model would have a low standard error of estimate. It would have a high coefficient of determination. So this would mean that the regression explains a lot more of the variation than the errors do. And similarly, F-statistic, same thing. F-stat is the ratio of the regression explanation relative to the error explanation. So if you see this, it means that the model has a strong explanatory power. However, these statistics, so the standard error, coefficient of determination, and F-stat, are calculated using in-sample data. In other words, the same data that was used to construct the model. So imagine this, right? So suppose you're looking at 100 observations. You use that 100 observations to construct the model, but then you would calculate these stats using those exact same 100 observations, right? So therefore, this leads us to step 4. So to determine the model's forecasting accuracy, you look at errors generated when the model is run using out-of-sample data, right? See, here's how it works. When you're using a data set to construct the model, by definition, will be the line of best fit. So of course you're going to get the best results for these statistics, right? Because when we calculate the beta 1 and beta 0, it's trying to make the best fit through the data. So of course the in-sample data is going to result in some very favorable numbers for these stats. But then you got to ask yourself, right? Even if you're not a quant person, it's just logical. You got to ask yourself, well, okay, well, how well would this model perform using a new data set? In other words, data that wasn't used to construct these coefficients. And that's where step 4 comes in, right? So then, because we're using out-of-sample data, we would look at what's referred to as root mean squared errors. And root mean squared errors, it's the definition is very similar to standard error of estimate. What's the difference? SEE is calculated using in-sample data, whereas root mean squared errors is calculated using out-of-sample data. So the lower the root mean squared errors, the greater the forecasting accuracy of the model. And again, ladies and gentlemen, even if you're not a quant person, what's the key word in root mean squared errors? Errors. So if someone tells you that this model has lower errors, even if you don't know what's happening with in-sample and out-of-sample data, that should set the tone for the answer. Lower errors means greater forecasting accuracy.